It's when you have a variable, they become square. Tom, go.
Y is equal to ax squared plus bx plus c.
Awesome. Very, very nice. Good, good. That's the general one. I want to come back to that one if you don't mind. I want to make up a really simple one. I want to compare quadratic to linear, because linear models and quadratic models are actually subsets of the same type of equation, whereas exponential is very, very different. So here's why. Let's make up a very, very simple quadratic example. X, y, and let's make the y just be the simplest possible we can think of, y equals x squared, just to make life easy for ourselves. Very, very simple. Let's run some values through it. Oh, 1, 2, 3, 4, and it continues ad nauseum. If x is 0, what's y? 0. Gotta be, right? If x is 1, what's y? If x is 2, what's y? Okay. Is there any kind of predictability in those y values? I mean, you can tell me, obviously, if x is 5, what y is, right? But suppose, for example, we're doing this a little bit backwards. I started with an equation, didn't I? Imagine that you didn't know that that was y equals x squared. Is there any pattern in those values that exists? Now, you have to think outside the box a little bit. I'm sure you didn't do this when you learned these in 95 and 60 and 65 before. Is there a neat little arithmetic pattern that's going on? And Katie's saying, yes, it is. Katie, what do you see?
2, 3, 4.
2, 3, 4. What's 2, 3, 4?
Where?
No, look at the y values, not the x values. Thank you, sister. Not the x values.
Dang it.
Not these.
They're all multiplied by themselves.
True. Good. Think simpler. Don't think multiples, think adds. How do you get from, thank you for that. How do you get from one to the next? So for example, to get from 0 to 1, how far apart are they? They're 1 apart, yeah? How about from 1 to 4? How about from 4 to 9? How about from 9 to 16? So you see, even if you didn't know that it was y equals x squared, could you predict what the next one would be? You would know that it would be what? It has to be 25, because 25 is 9 up from 16. Now what the hell? That's kind of cool, huh? That's kind of cool. It's kind of cool because look, these are now 2 apart the entire way, yes? These, if you go out one more, 2, same color. 2, 2, 2, 2. Isn't that, well, because 1 to 3 is 2, 3 to 5 is 2, right? Now, compare that to a linear model that we've been playing with the uninsured, with Facebook, with some other data we were playing with. Compare the Mount Bachelor ticket prices. Compare that kind of model over here with linear. And again, 0, 1, 2, 3, 4. Let's just make up a model. I'm going to call 0, 3 is the first one. Which of this would be? 1, what? Your choice. Give me the number to go right there.
6.
6! Okay. What's the next one going to be? If this is a linear model, gotta be, doesn't it? What's the next one? What's the next one? You're doing it. Nobody asked what the equation is, did you? Nobody asked what the equation. We didn't have to ask what the equation was. Even though it looks like it appears it's y equals 3x plus 3. But you don't need that, do you? Because you know, what does a line have? A constant slope. So once you know these are incremented by 1, these are your runs, correct? These are the rises. A line has to have constant slope, constant rise over run. So once you've established that this is 3, what does this have to be? If it's linear, it's got to be 3, and this has to be 3, and this has to be 3. Now the technical mathematical term for those are called first differences. I want to mention that from time to time in class, the idea of that. These are called the first differences. We'll put it up here. These guys right here are called the first differences in the y values. And the beautiful thing about linear data is it demonstrates a roughly constant first difference. That's the point. That's Tawny's constant slope. If you have constant first differences, then you arguably have linear data. Now, constant is a tricky one to measure. You have to measure what constant means. Those are perfectly constant. 3, 3, 3, 3. Perfect. So what is arguably? Well, we'll develop that as we go through the next 6 weeks together, I promise you that. The idea of statistical evenness, statistical equality versus 3 equals 3. Well, 3.1 might be close enough to 3. No, but 3.1 is bigger than 3. Well, statistically, it could be arguably the same. No! Don't worry. I'll put you at peace with that, I promise. But the idea is, when you see the first differences be roughly constant, then you know you're most likely looking at linear data. So what happens when you don't? I don't think we see that with the bike data, do you? We definitely don't see that. Well, you have two choices. You've got exponential and you've got quadratic. Now, quadratic, here are the first differences right here, yes? Those are the first differences. The second differences are constant here, aren't they? That's what these guys are. These are the second differences. And those, when those show consistency, you know you're most likely looking at quadratic data. So we have a choice here. We have a choice to run either exponential or quadratic models. I'm going to go with quadratic because more of you have studied that. Only 1 or maybe 2 of you have studied exponential models. So I say let's go with quadratic. The math is going to be easier, first of all. There's no real reason to pick one over the other, except for there's one reason you might know to pick one over the other. Quadratic is the better of the two to use. Anybody know why? This requires some physics to know the answer to this, just so you know. So if you haven't taken physics in a long time or ever, you might not know that. When you drop something on Earth, it's subject to gravity. What is the force of gravity? It's okay, you don't remember. It's okay, Tony. It's 9.8 meters per second squared, which is one of those constants that you forget because who cares? All you know is if you pick both feet up, you're going to fall down. But that same force is pulling me on my bike down the hill, right? That's the idea. So I know there's a force of gravity pulling me down, so I know quadratic is a pretty good model because it's quadratic, meters per second squared. Nothing about an exponential power going on there, except for second squared, which is quadratic. So based on those two things, based on the fact that gravity's working on my bike, and the fact that most of you have done quadratic models, let's stick with this for now. We'll come back and do exponential models soon, I promise. I promise, we'll do those as well. I mean, they're all worth doing. But see, that's where we're sitting right now, and especially with some of the questions we were getting with the exponential before, we'll go back and spend more time on that. Let's go into quadratics. So here's what I want us to do. I want to come up with a model of that situation we just had. I'm going to pull my data back down, grab TIs.